Okay, hello everyone. As you can see, I'm not Professor Graffi. My name is Andreas Disterhöft, and Professor Graffi is not here. He's on a conference in Qatar. So I will hold the lecture today and tomorrow. Okay, all right. So last lecture, Professor Graffi presented Geodemia, a location-based overlay using Doom filters. And before introducing another location-based overlay, I would like to present a real-world scenario using Chord. This is web peer-to-peer, which I implemented in my master thesis. First of all, what is web peer-to-peer? It's a prototype of a secured browser-based social network. And it is built on top of a peer-to-peer framework, which is based on Chord. So it's a secured peer-to-peer social network. And the great advantage is, so over other peer-to-peer software, is that we don't need to install any software, because it's you only need your browser. Because we use WebRTC. WebRTC is the web real-time communication. It is a standard created by W3C to enable browsers to communicate directly. So after a connection has been established, data or audio-video streams can be sent using this standard. Yes, the peer-to-peer communication between browser instances is allowed with this standard, and this creates the possibility to establish peer-to-peer overlays. This is what we have done, and here you can see our modular software architecture, and we are interested in the web DHT overlay module, which is on the bottom, which includes a Chord implementation and a security layer. First of all, I want to talk about the Chord core, which is an OpenChord fork, and I want to briefly present how we changed the OpenChord implementation. First of all, we added a monitoring and a security layer. The monitoring layer was only for evaluation purposes for my master thesis, and the security layer creates an PKI with self-signed certificates, and the idea is to use public keys as Chord IDs. So how to do this I will explain on the next slide with the security layer. Also, we heavily modified the following. First of all, the OpenChord implementation is in Java, and yes, we wanted to create a web application, so we had to port it. And GWT, which is the Google Web Toolkit, creates this possibility, so we can create web applications by programming with restricted Java RPs, which are translated in JavaScript during compilation. Another nice feature is that other JavaScript libraries can also be used via GSNI, which is the JavaScript native interface. Yes. On the communication layer, we had to modify the existing protocols because we wanted to use the WebRTC, and we also added some social network building blocks, for example, a user search in our Chord ring. This is equivalent to a certificate search, which we can see on the next slide. And we also implemented application messages, and we use the Chord ID to address nodes. So we can for example, send chat messages, body requests, or audio-video requests with this application messages. In our security layer, we use the asymmetric cryptography, the ECC, which means Elliptic Curve Cryptography, in order to offer a deterministic login. We derive the private key out of the input, so the username and the password. Then we derive the public key out of the private key, and we set the Chord ID as our public key. To do this, now we can send encrypted messages to other peers using the receiver's Chord ID, because this is the public key. And we can add a signature to these messages, and the receiver is able to verify this message by using the sender's public key. Also, we have a few different types of DHT entries. We have 3 categories: the unsigned, the signed, and the encrypted. Yes, for example, we use encrypted DHT entries for saving contact lists and chat histories. Another feature of the security layer is the creation of self-signed certificates. These certificates contain contact details and the Chord ID from the peer, which are signed and located at well-defined locations. First of all, at the concatenated hash of the username. This is a logical username list in our DHT, and it is also located on the hash of the public key. So every user has to care about its certificates availability, and this is important. So peers can be searched by other peers, and they can establish a contact by using the Chord ID. Now so here's first of all a screenshot of our application. They also want to show a small demo. I hope the Wi-Fi connectivity is very poor here. Okay, this is the login mask. It's very easy and simple. First of all, we type in a username and a password. For example, I type in Andi, password. Then we want to, so we have to decide whether we want to log in or register, because we didn't register this account. We want to register this first. And then we have to choose whether we want to join the public network or the private network. The private network, so if you choose private network, you have to type in a bootstrap ID. Yes, to join a Chord ring. The public network, in the public network, the web server provides a list of bootstrap IDs, so you can join the public network. Okay, so you can try. Okay, all right. So this is my contact list. I have nobody in there, so I create just another one. Okay. Now we can search for Lena, for example, which we just added. Here is Lena, and we see, okay, here's Lena with first name and last name and age not defined. Yes, we can add her to the contact list. And on the other side, we get a notification whether we want to add this contact. We can let us, so we can see the certificate with the public key. So we can, for example, check this public key first, because these are self-signed certificates. So it's better to check the public key first with a signature. And okay, so let's accept this. And then we have someone in our list, and we can start to chat, for example. Okay. Another feature is now that we can also start an AV stream, and yes. Yes, we want to stream. Okay, so yeah, the right below, this is my stream, and the left side, it's the stream from the remote. So this is the same in this scenario. Okay. Also, we have here some interesting infos about the local repository, for example. Here we have the DHT entries of our node. So we can see, for example, this entry is a certificate from Andy with a compressed public key and so on. Yes, and for example here we have reference tables. So our routing table, we are this node. And yeah, we have just one entry because we have, and this is also the predecessor, so we just have two nodes in this network. Okay, the interesting thing is that we can log out and log in again, and the contact list is yeah, we can get the contact list from the chord tree. I hope this works. Okay, so we got the contact list with Lena and the chat history. Okay, all right. Yeah, I want to encourage you to use this for a beta alpha test. It can be reached via web-peer-to-peer.cs.uni-Düsseldorf.de. And yeah, a bug tracker is not yet implemented, but I would appreciate a bug report via email. This would be nice. I can give you my email address, so you can just send me a bug report. Okay. All right, and the last hint, smartphones are not yet supported. But I will implement the support in the future, because yeah, we have there no click events, we have the touch events and so on. Okay. So now the next topic is the Globase.KOM, which is a location-based overlay and supports heterogeneity. Yeah, this slide motivates the heterogeneity. Previously, we saw that all peers in the most structured overlays like Chord, CAN, or Cademlia perform the same operations independent of their capacities and without an hierarchy. Heterogeneous overlays consider heterogeneity, and they introduce roles for stronger peers. These are super peers in most cases. Here we have an agenda, and we are over there. Okay, so Globase.KOM is the geographical location-based search, and here we have, we want again, like in Geodemlia, to provide location-based area search without the use of a DHT. Yes, so we want to find all peers in a given zone, or the closest peer to a given point. Globase uses a supernode-based structured overlay, and it uses a tree structure where inner tree nodes are supernodes. But we will see this on the next slide, and yes, we will see how to construct and how to use this hierarchical overlay. So this is an overview slide of Globase.KOM. We have a super peer-based n-ary tree. We have here different roles for peers, which is supporting the robustness. And yes, we have a structure where the super peers are responsible for a rectangle zone, and these zones lies within each other. So for example, we have here a Globase overlay, but we will come to this later on. We have interconnections which are used to enhance the robustness of the tree in case of failure and to reduce load and delay. And similar to Geodemlia, the Peer ID contains the peer location and super peers zone. Okay, first of all, the super peer based n-ary tree. Like I said, each super peer is responsible for all peers in the recognized zone. For example, we have this peer K. He is responsible for these two peers, and we can see this in the tree structure. He is K. Okay, here 3, I don't know why 3, but he should be responsible for these two nodes. And for example, A is responsible for the whole Earth, but he has only some peers outside the other rectangular zones. For example, this one, this. Okay. Yes, a peer is called the parent of a other peer when this peer zone is inside the other peer zone. So, for example, E is a child of A, or the other side way around, A is a parent of E. Now we want to clarify how the n-ary tree is constructed. First of all, we have one peer in our overlay. He's joining the overlay, and he is somewhere in Africa. This peer is our peer A, and the zone is the complete Earth. Here we have the tree structure, and we have a super peer load. Every super peer has a load, where he has two thresholds. the L1 and the L2, the lower and the upper bound. So now a few other peers join, and the load is increasing because the load is defined to be the number of nodes super peer maintains. So for example, we have here 5 nodes now. If a few other nodes join now, the super peer load also increases and may reach the upper bound. If the upper bound is reached, we have to split a zone to reduce the load, because it's important that the super peer's load should not exceed the L2. So the load difference is between L2 and L1 is released every time the super peer reaches this L2's threshold. So for example, we build this zone with a few nodes and we reduces the load. So we are now on L1 again, and we have a peer. Yeah, the peer has been decided to be the super peer. This is the B. P here is the strongest one in this rectangular zone. So he is now another super peer, and A has a connection to him, and A is the parent of B. Now a few other peers join the overlay, and the overlay can look like this. For example, here we can see that B has another rectangular zone because the load was too high for B. Now F has a lot of peers. Also on the Asian side and on the American side. Okay, here we have some other examples for different thresholds with 1000 peers, which are distributed throughout the Earth, respecting popular density. The first image, the upper one, here we have the L1 threshold set to 5 and L2 set to 10. So a node is overloaded if it maintains 10 nodes. So this is why we have a lot of zones here. I hope you see this. Over there we have a lot of zones. So here we have a tree with 252 super peers. On this example we have L1 set to 50 and L2 set to 100, again 1000 peers. And here we have only a tree with 14 super peers. Just an example to understand this. Okay, so how do we communicate the tree structure in Globase? The Peer ID contains everything relevant for its position in the tree. The GPS coordinates tell a node's physical location. If the peer is a super peer node, the second part contains its zone of responsibility, and this is coded as with an origin concatenated with the horizontal length and the vertical length of his zone. The last part is a random part to support more than one node at the same location, because if a node is not a super peer, then the second part contains only zeros, so that's why we have a random part. Okay. So the advantages are that we can determine super peer responsibility for a given point without contacting him, only by looking at his peer ID. And we have a controlled peer ID assignment process. Now we have the tree structure, but what can we do if a node goes offline? For example, if peer H goes offline, then this tree with LMN as super peers will be cut off from this tree. This is why we need interconnections in this tree structure, and there are two different interconnections. The first one is the high interconnection. This is this is for increasing the robustness, and yes, so we want to know about the grandparent. So if our parent leaves the tree, we have a contact to the grandparent. And we have, so the other interconnections are the wide interconnections. These are for efficiency, and they help in case of degenerated trees to route to appear faster. Yes, the purpose is the failure recovery for the high interconnections and a more efficient search for the wide interconnections. And theoretically, the idea is to transform the tree structure to an extended graph. So, how we get new connections, new interconnections? We just learn from received messages or obtaining from neighbors. Also, it's only a recommendation. So there does not exist a fixed number of interconnections each node must maintain. So we just learn from other peers by getting information. Okay, now we want to understand how to start area search. So how to get all peers in a defined area. First of all, what is the input? So we have the search information with a center and a radius, the query initiator and its responsible superpeer, and the sequence number which is used to avoid duplicate responses. Now I want to show an example with no interconnections, so just routing in the tree structure. So we have this green node now, which wants to start a query to this area. So we have this green node, and we want to know which peers are in this area. The query is forwarded first of all to our parent, and our parent first of all checks, okay, is the whole area inside my zone? No, it isn't. So we forward the query to our parent, which is A. A is the one who is owning the whole area, so for sure this area is inside his zone, and he forwards the message to the zone which is covering this area, which is the zone D. You can see it in the tree structure here over there to D, and he covers the whole area search area, and it knows that K and J also have a part of this area, so it forwards the query to K and J. Here we can see this. Okay, and for each received, and the response, sorry, the response is also forwarded the reverse way. So we just give it the way back. It's not very efficient, but okay. For each received message, also interconnections are kept to improve the next query, for example. Here we have another example. We have this node somewhere in the USA, J. No, this is not J. J is its parent. And we want to know about all peers in this area. And the steps are like before. First of all, we forward the query to J. J forwards the query to D. D forwards the query to A. A knows, okay, I have some peers in my area, so I can send this to D again, and I contact E, C, and B. And B checks whether he has some other zones which are covering this area, search area, and this is, for example, F's zone. And yeah, here we have the structure BCE, BCE, and F. Okay. In contrast to Geodemia, where we cannot be sure that we found all nodes in an area, in Globase we are, because of this tree structure. Okay, here we have the evaluation of Globase, which offers a location-based search without a DHT and utilizes heterogeneity. The benefits are we use a fat tree structure, so strong peers are at higher positions in the tree. We have no peer overloaded in normal case, as the maximum load of L2 is not exceeded. Yes, we have interconnections which are used to stabilize the tree structure and to fasten the search. And we have an area search in O log n. And the drawbacks are the following. Yeah, we have complex interconnections, so we got no specification on the interconnections. So if we pick them unhappily, a node might have no advantage with these interconnections. And the protocol describes only the tree growth, but not the shrinking. So, for example, if we have churn on, and we might have to shrink a zone because there are some nodes left, and yeah, this does not exist simply. And the last one is the limited functionality, because we have only an area search. Also, a very big drawback is that the load in Globase is defined as the number of nodes a peer maintains. But if we don't use any interconnections, or for example we picked some unhappily, the root's bandwidth may be exhausted, because every query, not every, but the most queries will go through the root. And so the main load may be another load than we focus on here. Okay, now we come to the next topic, which is adaptive heterogeneous chord. The short form is AH-Chord. Here the authors wanted to show how chord can be modified to make use of heterogeneity of peers. First of all, we want to check the issues with chord. We have a performance issue because we only use unidirectional lookups, but this we will not challenge with AH-Chord. The other issue is that chord is homogeneous, so all nodes are expected to be equal, and also request patterns are often zip distributed. This means that there does exist popular data, which is maintained by a random node, which may be overloaded because this is popular and a lot of nodes request this data. So how can we fix this? Yes, we could enable load balancing, but still there does exist a lot of discussion how to define load. For example, we saw in Globase, we have defined load as the number of nodes a superpeer has to maintain. But this is maybe not the critical load. For chord, load may be defined as the number of objects a node has to maintain or is responsible for, or its ID range, or maybe the traffic for providing the objects. This is maybe the one which is the best because it requests in general are zip distributed. Also, we have the node capacity, which is defined by the bandwidth and the storage space, but the storage space is not critical because storage is cheap nowadays. Okay, here we want to discuss the load balancing versus the quality of service in an overlay. How to balance the load over all peers. At this point, the quality of service is irrelevant. So there does exist some goals like a node. The node load should be almost equal for all nodes. This is somehow homogeneous. Then we have a goal, the node load should be proportional to the node's request frequency. So for example, if someone is requesting a ton of objects, then this node should also provides some work. Yes, this is practically a good solution because strong nodes can offer and the last one, we have the node load proportional to the node capacity, which is the maybe the best one to support the heterogeneity of peers. Here we have the quality of service. The main goal of applications is to minimize the number of overloaded peers. So the overall service quality is the best. Here the load imbalance of peers is not relevant. In adaptive chord, the aim is to minimize the number of overloaded peers, so we get the best service quality. And a peer is overloaded if its bandwidth is exhausted. Okay. Here we want to assume a usual use case for chord, a DHT for file object storage with a typically file size of 0 to 10 megabyte. For example, this could be a file sharing or peer-to-peer based social networks. And also we know that the requests are zip distributed, so we have popular files, and these popular files may change over time. An original chord with homogeneous nodes, we just assign files randomly, so nodes may be overloaded. Adaptive chord acts differently. Here we have an additional capacity overlay, which is mentioned here, where the heterogeneity is considered to not overload peers. How this works we will see on the next slides. Okay, so we have two overlays in adaptive chord. We have the routing overlay, like an original chord with normal peer IDs and object IDs, like Professor Graffi mentioned. With with a modification, we have now a modification that we introduce mirrors. Mirrors are peers which can be asked to host an object. So if our node is too weak to host an object, we can ask mirrors to host this object, and all requests are forwarded to this mirror. Okay, and the second overlay is the capacity overlay. This is used to find a mirror node if you are overloaded or your node is overloaded, which covers the bandwidth needs. So the second overlay is like another chord ring, but the peer ID is different. Yes, the peer ID is different because it contains the own free bandwidth capacity, and is calculated by this formula. It's not that interesting, but we have this capacity overlay with a normal chord overlay and other peer IDs. So this is the main difference between both overlays. And how can we combine both overlays? So how can we choose mirrors? Yes, as every node is member in both overlays, which only differs in the calculation of the peer ID, we can choose a mirror from the second overlay whenever we are overloaded. For this, we request, we find a mirror on this capacity overlay by searching for a bandwidth capacity we need. So we need to fulfill this requests. So afterwards, all requests are forwarded to this mirror to save own bandwidth. Okay, now we have some simulations of the adaptive chord. The simulations are all with 3000 nodes, and chord is always the right graph, and adaptive chord is the blue one. The green